Okay, welcome back to our next lesson. This begins on, begins on page 9 in your notes. And this one is called the double angle formula. And we're going to see double angle formulas for sine and cosine and tangent. These formulas are also provided on your formula sheet, so you don't have to memorize these again, but you have to know how they're used. Okay, so here's the three formulas right here. Actually, there's one formula for sine of 2 times some angle alpha is equal to 2 times the sine of alpha times the cosine of alpha. Notice clearly why they're calling it double angle formulas, because you'll notice that the argument in these cases are all 2 times some angle. Now they're using alpha, but of course any symbol can be used for the angle. Notice that there are 3 different versions of the double angle formula for cosine. Um, Depending on what you're trying to do with them, if you're trying to, for example, prove some identity that involves the cosine of 2 times an angle, you have to look at the 3 versions of the formula very carefully and decide which one would be the appropriate version to use in a proof, for example, and for trigonometric identities. And then there's the tangent double angle formula down below. There's only one version of that one as well. So let's have a look. There's a couple of problems on page 9 that we're going to have a try with. All right, and here's one. The very first one there, example number 2, part 1, just says to simplify that the cosine squared of alpha minus the sine squared of alpha. You're asked to simplify that. Now you'll notice that's actually one of the versions of the double angle formula for cosine, isn't it? And they want you just to simplify that. Well, what they mean here, all they're doing is they're kind of working backwards and showing you that it's actually equal to the cosine of 2 alpha, right? Or in fact, you could even prove that it's equal to one of the other versions. And that's what they've done here. Now, the proof that they've done is they've taken the cosine squared of alpha, and using one of the Pythagorean identities that we've seen previously, they've replaced that with 1 minus sine squared of alpha. That, again, is just one of the Pythagorean identities we saw previously. And now, of course, you'll notice that this expression involves sine squared alpha twice. So you can actually combine those and get 1 minus 2 sine squared alpha, which you might notice again is just another version of the double angle formula for cosine. And then they're saying is equal to the cosine of 2 alpha. Well, because obviously it is. It's one of the versions, but you could have said that right back from the beginning. You can also make a substitution here. If you were to replace sine squared alpha in the original problem with 1 minus cosine squared alpha, you'd also end up with uh, this second version of the double angle formula for cosine. So that's just a pretty simple, pretty basic type of question. Let's look at number 2 right here. Okay, now this one is a proof. When it says prove, like this, or if it said verify, that's also a proof. Now we have to take this and we have to show that the left-hand side is equal to the right-hand side again. Now remember, in a proof, you work with one side only. You pick the side which looks like it's more complicated, and I think the side that actually looks more complicated here is probably the left-hand side. In fact, I know it is. So let's start it by this proof by writing down what the left-hand side is equal to. And remember, we're going to use other identities that we've learned, basic trig identities perhaps, different formulas now that we've also learned about, just plain algebra. And we're going to try to take that left-hand side and simplify it. So we have 2 over 1 plus the cosine of 2x. Now, notice, let me just get a different color here. Notice this thing right there. Look at that. The cosine of 2x. That is double an angle. The angle in this case is x, but it's the double angle formula, isn't it? So you're going to have to use one of these 3 versions right here, okay, one of these 3, to try to prove this. Now, which one would be the appropriate version to use, I wonder? Well, if you look at it carefully, remember I said one strategy that you should always keep in mind, that you should always think about, is look carefully at what you're trying to prove it equal to. Look at that very carefully. It's secant squared, isn't it? Eventually, that's what I want to end up with. Well, secant squared is really 1 over the cosine squared. Now just keep that in mind. Just keep that in mind as you're doing this proof. In other words, you want to end up with an expression that has cosines on the bottom, cosine squareds, hopefully, but you don't want sine squared there or anything like that. So if you were to replace cosine 2x and try to avoid any expression that contains sines, which one is the obvious one to use, I wonder? Let me just erase all this. Which of these three versions is the obvious one to use that involves cosine but not sine? I'm thinking maybe this one might be the appropriate one to try. So let's go ahead. Let's make that change. We will replace the cosine of 2x with, let me just come down here a little further. We'll replace the cosine of 2x with, let me just write it in, 1 plus, now use brackets. Here it doesn't matter, but if that was a minus in front, it would really matter. 2 cosine squared x minus 1. All right, so that all I did there was use my double angle formula for cosine. I'm trying this one to see if it works. If it does, wonderful. If it doesn't work, I'll try something else. Now, remove the brackets in the denominator. And really nothing happens here because there's only a plus in front. You don't have to use your distributive property or change signs or anything like that. It just becomes 1 plus 2 cosine squared x minus 1 when you remove your brackets. And of course you can see now that the 1's cancel out. This 1 and minus 1, they are gone. So you're left with in your next step, it's just 2 over 2 cosine squared x. Now, look at that carefully. What do you think you can do there? Remember what you're trying to prove it equal to. Right up there at the top. See that? And by golly, we're almost done. The 2's cancel because they're both factors. All right, so you're really left with 1 over cosine squared x. And by golly, if that's not secant squared x, I don't know what is. That is definitely secant squared x. And look at that. That's what you were trying to prove it equal to. So equal to the right-hand side. Left-hand side equals right-hand side. And this proof is now complete. You have verified that identity. You have proven that it is true for any values of x, for any angle, as long as the ratios are defined for those angles. Okay? And you're going to be seeing in just a little while some other proofs, practice pages, and you're going to be using the double angle formula for some of them, not for many, but for some of them you'll see that. Another type of problem that you may have to use the double angle formula for is this one on the bottom of page 9. Now this is not a proof. This is not a proof. This is actually similar. This is actually similar to the types of problems we were doing in our last video, in our last lesson, using the sum and difference formulas. So this one says find the sine of 2x. And again, remember now, I want the exact form. No decimals. All right, no decimals. Your answer could be just a fraction, or it's even possible it could be a radical. Okay. Now, notice they're asking you to find the sine of 2x, which means if I were to just write the formula down up here somewhere, let me write it over here. Sine of 2x. Now, according to this is the double angle for sine, you see. So the formula says that's equal to 2 sine x multiplied by cosine x. That's what it tells us, isn't it? That's what it tells us. It also tells us that this angle x is in quadrant number 1. So what I'm going to do here is make another simple little diagram like I did previously. just smack an angle down in quadrant number 1. Notice you're told that the cosine of that angle is 4 over 5, and that means I'm going to be able to fill in a couple of the sides in that triangle. We're going to make a triangle, you see. So in that regard, this question is not that different from what we were doing in our last lesson. The only thing is now, I know what cosine x is. It's 4 over 5. The only thing I have to find is the sine of x. So there you go. Make a dot, make a point somewhere on that terminal arm. Drop a perpendicular line down to the x-axis. Here is your angle x. All right, and because it's in quadrant 1, the reference angle really is my x. It's the same thing. So using that, right in now, put in the two sides. One side must be 4 and the other side must be 5. Okay, and remember that the cosine is adjacent over hypotenuse. So the adjacent side is the 4, positive direction, so it's positive. And the hypotenuse is 5. And look at that, there's your missing side. Now you need to get that missing side, again, using Pythagorean theorem. So put any variable there you like. I wouldn't put an x there again, by the way, because x is your angle, isn't it? Put a y there, or a w, or any symbol you like. Put a happy face there. Happy face can be a variable. So using the Pythagorean theorem, you're going to have 5 squared equals w squared plus 4 squared. And like I say, you've used Pythagorean theorem before. This should not be a difficult type of calculation. You're going to have 25 equals w squared plus 16. You bring it over and you're going to get a 9. 9 equals w squared. You take the square root and look at that. No radical involved here. W is equal to 3. And because that side is actually going upward from the x-axis, it really is 3. It's positive 3 right there. Okay? And now you can see what the sine of angle x is. Let me just put that right here somewhere. So the sine of angle x is equal to the opposite over the hypotenuse. So in our case, that's going to be 3 over 5. All right, so if anything, this type of problem is even less involved than what we were doing in our last lesson, because I only require one diagram here, only one. But now I can go ahead, everybody, and I can actually fill in these ratios here. Now remember to use the exact values, fractions in this case. If there were radicals involved, square roots, then just keep your square roots there. Your calculators, most of your calculators, Casios I know most of you are using, they can handle radicals anyway. So the sine of x we just calculated, that's 3 over 5. Okay, and the cosine of x we were given, that's 4 over 5. And if you type all this into your calculator, those fancy calculators you've got these days, that'll just give the answer right back to you anyway. But if you're doing it the old-fashioned way, like me, you're just going to multiply 2 times 3 times 4. That's 24. And 5 times 5 in your denominator. You actually do multiply those, remember? That becomes 25. So there's your exact answer. If that reduced, I'd definitely reduce it. All fraction answers must be reduced. And there we go. I found the exact value of the sine of 2x using the double angle formula. So like I say, very similar to the types of examples we were doing in our last lesson, okay? So I'll stop this video there. I'll start another video now in just a moment on the half angle formula, which begins on page 10, and then I'll be able to assign some extra practice problems for you to go ahead and try, okay? So I'll stop there, and we'll pick it up in just a minute. Bye-bye.